This lesson will serve as a review of atoms, ions, and molecules. A lot of the things covered in this particular video lesson are things that we discussed in Unit 1 or things that you already know from earlier science classes, but it's a good way to lay some foundations for Unit 2. You can see the list of learning goals here below. Take a moment, pause the video, and mark these as part of Unit 2 on your yellow objective packet. You will notice that some of them are objectives we covered as part of Unit 1, and they should be indicated to be part of both Unit 1 and Unit 2. We're moving on from nuclear processes. We've looked a bit into what it takes to make a stable nucleus, and now we're going to start looking at processes that are chemical rather than nuclear. The nucleus is pretty easy to visualize. However, the behavior of the electron is a lot more complex. Next semester, we're going to spend an entire unit describing the behavior of the electron, but for now, we're going to settle for simply stating that the electrons are outside the nucleus and relatively far away by comparison to the size of the nucleus. I've given you a little perspective here in terms of thinking about a hydrogen nucleus being the size of a basketball and putting that basketball at the center of the Earth. You would find that the electrons are buzzing around somewhere in our upper atmosphere. The distance between the nucleus and the electrons makes it rather easy for an electron to be gained or lost by an atom, and that really is at the heart of chemistry. There's a very, very important rule to obey when you're dealing with chemical processes, and that is that the protons and the neutrons are never gained or lost by the nucleus in a chemical process. All the action is with the electrons. Now, this is a change in mindset from last unit, because last unit we dealt with the nucleus, and you were allowed to change how many protons and neutrons as the nucleus underwent radioactive decay, or fission, or fusion. But here in our chemical processes unit, all the action is going to be with the electrons. The primary difference between chemical and nuclear processes is that chemical processes conserve mass and energy separately, while nuclear processes allow mass and energy to be interchanged according to Einstein's equation. Moving forward with this class, we are going to focus primarily on chemical and physical processes rather than nuclear processes. In the first unit, we talked briefly about the atom, and just remember it's the smallest unit of matter that retains the properties of that element. The identity is determined by the number of protons, and by definition, the atom is electrically neutral and must have the same number of electrons as what it has protons. We also talked about ions. Ions are what you get when an atom gains or loses one or more electrons. And it's important here that you only change the number of electrons. You cannot change the number of protons because that changes the identity. Our ions always have a little charge denoted up here in a superscript position. So for example, Mg2 positive lost 2 electrons, whereas Br1 negative gained 1 electron. You will sometimes see the 1 written next to the negative. Sometimes you will not see the 1 written next to the negative, but if there's if there's no number there, it's an implied 1. Remember that things are positive when they lose electrons because electrons are negative. They're negative when they gain electrons for that same reason. We learned that cations are positive, and here's a picture of a smiley cat to help you remember. And cations are always formed from metal atoms. Since you know where the metals are located on the periodic table, you can predict which type of elements are going to make cations. When we name the cations, the naming rule is very simple. You just use the element name followed by the word ion. There's no need to indicate in the name of the element what the charge on the ion is, because we know that the charge on the ion is determined based upon the column in the periodic table. Potassium is in the first column, so it's positive 1. Calcium is in the second column, so it's positive 2. Our anions, we used a picture of an ant to remember that they're negative, are formed from nonmetal atoms when an atom has gained a negative electron. Naming anions is only slightly more difficult than naming cations. We simply are going to change the element name ending to be IDE and add the word ion. So we have the oxide ion and the bromide ion. Notice again, there's nothing in the name to indicate that oxide is -2 and bromide is -1, but we know that based upon the position of these elements in the periodic table, and therefore we don't need any kind of an indicator at all. We also learned in the last unit that our monatomic ions, the ions that form from a single atom, we can just look at the periodic table, and the charge depends upon the column in the periodic table. So we numbered our columns at the end of Chem Activity 2, and you may even want to take your large periodic table and put in pencil some numbers up above. +1, +2, +3, plus or minus 4, -3, -2, and -1. That will help you remember when you're working with your periodic table that you really already know the charges on the different ions. And that's going to be critically important in this unit. The tricky set of ions are going to be the transition metal ions. We really haven't dealt with them before because they're a little bit unusual. They're always positive on grounds that they are in fact metal ions, but they can take on a variety of different charges depending upon their environment. For example, iron can come as iron with a +3 and iron with a +2. We can't call them both the iron ion because we wouldn't have any way of knowing their charge. So the system that has been decided on is a very simple system where you use a Roman numeral in parentheses to indicate the charge on a transition metal ion. This was decided by IUPAC, the International Union for Pure and Applied Chemistry. They've made this change from a more complex system where they used suffixes like "ik" and "us" to indicate which one had the greater charge and which one had the smaller charge, but the "ik" doesn't necessarily mean +3 and the "us" doesn't necessarily mean +2. So this old system really doesn't get used anymore. It's not going to be the system that we use in this class, and it won't be a system that you use anyplace else. All modern day chemistry is done using the simpler IUPAC system of simply using the Roman numeral to indicate the positive charge. There are 3 exceptions to the rule about the transition metals having a Roman numeral in their name, and they are silver, cadmium, and zinc. Unlike the other transition metals, these 3 ions only take on one charge, so they don't need a Roman numeral in their name in order to indicate the charge. Ultimately, you're going to have to just learn that silver is always +1, cadmium is always +2, and zinc is always +2. Now, there is a way to look on your periodic table and figure this out. If you look in box 30, you'll see there's a little 2 above the zinc. Box 47, there's a little 1 above the silver. And box 48, there's a little 2 above the cadmium. While these numbers on the periodic table are not actually the charge, and I don't want you to use these numbers for the charge on any other elements, it happens that in the case of silver, cadmium, and zinc, these little numbers are the numbers that you need to remember for the charges. So if you forget, you can look on the periodic table and use the little number above those elements. There's another type of ion called polyatomic ions, which is kind of the opposite of a monatomic ion. A monatomic ion was formed of only one atom. A polyatomic ion is a group of atoms that collectively have a charge. These are ions that you're simply going to have to learn. There's not a lot of patterning here in terms of their names, but in order to do chemistry quickly and efficiently, you're going to need to know the names and the chemical formulas for the polyatomic ions. You will have a quiz in a few days here, and I will give you the name, and you're going to have to give me the formula and the charge. You will find a set of digital note cards on Schoology to help you learn these. You are responsible for the most common polyatomic ions, which are the ones above the shaded line in this little table. The ones below the shaded line are in use in chemistry, but not nearly as common, so we'll settle for just looking those up on this little table when we need them. Now, there's a point here of high attention that you need to pay attention to. And that is that there are three words that look very much the same: nitride, nitrate, and nitrite. When you're working with chemical naming, you have to pay particular attention to the last three letters. Nitride, which ends IDE, is the monatomic nitrogen ion, N3-. Nitrate is the polyatomic ion, NO3-, and nitrite is the polyatomic ion, NO2-. The same thing happens with sulfide, sulfate, and sulfite, as well as phosphide, phosphate, and phosphite. Now, one thing you might notice as we're doing this, the IDE ending always goes with the element once it's turned into an ion. And then there's the ate and the ite. If you look at the chemical formulas for the ates and the ites, you will notice that the ates and the ites have the same charge. The nitrate-nitrite group is -1, sulfate-sulfite is -2, phosphate-phosphite is -3. And you will notice that the difference between an ate and an ite is always that the ite has one less oxygen. And going from nitrate to nitrite, we go from 3 oxygens to 2. From sulfate to sulfite, you go from 4 oxygens to 3. And from phosphate to phosphite, you also go from 4 oxygens to 3. When I learned my polyatomic ions, I memorized nitrate, sulfate, and phosphate, and then I just figure out the ites by taking 1 oxygen away from the associated ate. So it's a shortcut that makes it a little easier to learn these ions. Well, our universe would be pretty boring if the atoms didn't get together to form compounds. Compounds are the substances that are formed when more than one type of atom gets together to form a molecule. A molecule is an electrically neutral combination of atoms that function as a unit. It is important that they're electrically neutral. They don't carry any kind of a charge. I've got pictures here of a couple of molecules. This is a familiar molecule, H2O. It's got an oxygen atom in the middle and a couple of hydrogens on the outside. This is a molecule called methane that you use more often than you think. This is the natural gas molecule. It runs the Bunsen burners in our classroom, as well as the furnace at a number of people's houses. You notice that it has a carbon on the inside, and it has 4 hydrogen atoms grouped around the outside. When you look at chemical formulas for molecules, the formulas tell you how many of each element are in the compound. So this molecule has 2 hydrogens and 1 oxygen, and so it has the chemical formula H2O. This molecule over here has 1 carbon and 4 hydrogens, so it has the chemical formula CH4. Not all molecules are compounds. Some of them are elements instead of compounds. We have a group of what we call polyatomic elements. These are elements that occur naturally as molecules with more than one atom of the same element. Hydrogen, fluorine, iodine, nitrogen, chlorine, oxygen, and bromine are all what we call diatomic elements. They always occur in pairs. Sulfur and phosphorus are unusual as well. They occur as S8 and P4. People sometimes refer to the diatomic elements as being the genuine elements. Things that end in gen and -ine are going to be diatomic. At this point, I want you to grab your big periodic table, and I want you to take a highlighter, and I want you to highlight the boxes for the diatomic elements. We're not going to include sulfur and phosphorus because while they are polyatomic, they are not diatomic. So we'll pick up hydrogen, nitrogen, all the way over to fluorine, and on down the halogens column through iodine. By having these elements highlighted on your periodic table, you'll be reminded on a daily basis that some elements occur in pairs.